Homework questions. I think we're good. Yes? All right. What we're looking at today is logarithmic to exponential form, going from a logarithm to exponential. Now, logarithms are inverses of an exponential. So an exponential function and its logarithmic are inverses of each other. Now, clear all that out. And clear all that out too. 10 to the x is an exponential function. Turn these two off. And if we graphed it, it would look like this here. So that's 10 to the x. Now, yes, this isn't in your notes, but log of x, log base 10 of x, would be this here. And these are inverses of each other. So we can go from one to the other. Now, one way that we can tell if a function is an inverse is if it's reflected across the line y equals x. So if we look at the blue graph, especially at the y-axis and going to the right, and our red graph are flipped across this line. So they are inverses. We can go from one to the other. They undo each other, actually. But the main thing we're going to focus on for especially this first part here is these two statements. Log base b of y equals x, if and only if b to the x equals y. So that means I can be given the logarithmic form and turn it into the exponential. Or we can be given the exponential form and turn it back into the logarithmic. We can go from one to the other. And this is helpful, especially when we start trying to solve these exponential equations. But for the most part, solving an exponential equation is fine, because we could say 2 to what power is 8? 2 to what power is 8? Well, that would be?
3.
Because 2 to the third is 8. So our value of x here is 3. So if we wanted to solve this here, we get x equals 3. And we could also say 3 to what power is 9? 2. So x is 2. And we could say 5 to what power is 10? Because 5 to the second power would indeed be 5 to the first is. So, as we know, and what we know so far, we don't have a way to write this or follow this and find its value. But it has a value. There is a value for this here. And instead of just leaving y'all with no answer, it might be helpful to give y'all an answer for this here. Because and we will go through this eventually, but it turns out it is this irrational number, 1.430676558, and it continues on. Is the value for x. What value of 5 we would need to get it to equal 10. And this is where logarithms are helpful in solving these where it doesn't work out nicely. Because if we wanted to solve the others, we could say that this is 2 to the third. This is 3 squared. But we can't do any of that with 10. But before we get anywhere to this, we're going to just focus on rewriting equations, these logarithmic equations, in exponential form. And again, log base b of y equals x if and only if b to the x is equal to y. We're switching from one to the other. Now, we're not going to have to do this every single time, but I do think it'll be helpful on these first few. B, X, and Y. We're going to state what these are. So if we look at this first one here, log base 2 of 16 equals 4. So looking at this here, what's our value of B? 2. Because it corresponds to our base of B. What's our value of X? 4, because our X is by itself, outside, on the other side of the log. And Y would be 16. Because when we write, because log base B of Y equals X, if and only if B to the X is equal to Y. So if we fill in the information we have, B is 2, X is 4, giving us 2 to the 4th, equals 16. That's it. Question on the first one. Now, the nice thing with these exponentials is we can check this, because I could say 2 to the 4th power and hit enter, and thus tells that it is indeed 16. Let's look at the next one. So we'll do the B, X, and Y again. For our second one, what's our value of B? 4. What's our value of X? And the Y is 1. So our B to the X equals Y. Well, the B is 4. 2 to 0 is equal to 1. So log base 4 of 1 equals 0, rewritten in exponential form, is 4 to the 0 equals 1. That's it. And again, we can check this in a calculator. We can take the calculator and say 4 to the 0 power, and it tells us it is indeed 1. Are you ready for the next one? Log base 12 of 12 equals 1. So we could do X, Y, or A, not A, B, X, and Y. But if we rewrote this as an exponential, what would we start with? So our base would be what? 12, and our exponent would be 1 is equal to 12. If writing out the value of B, X, and Y is helpful, do that. Write out B and X and Y. We don't have to, because our final answer for this is 12 to the 1st is equal to 12. How about the next one? Log base 1/4 of 4 equals -1. 1/4 to the -1. And that's it. Because here we're just rewriting an exponential form. Because normally, yes, we would want that exponent negative or positive because it's negative. But here we're just rewriting the equation. So we could put parentheses around our 1/4 to the -1 is indeed 4. If we want to go back here, yes. And again, we could write out the B, X, and Y so that we can see how it changes. We don't have to if we see how this works. Are we good with this here? Now we will come back to it later because there are properties of logarithms that we will see and learn that will help explain this even more. Most likely that'll be Tuesday, but we'll come back to it. Because at this point, it's easier to see this here, and then once we get used to the logarithms and their theorems, then we can start applying some of the properties as we learn them. All right, let's look at A. Log base 6 of 216 equals 3. exponential, it would be 6 to the third power is 216. How about our next one? Log base 7 of 1. So we would have 7 to the 0 equals 1. Because if there's not an exponent written, it's understood to be 1. So 7 to the 0 is a little bit different than 7 to the first, 7 to the 1. The only one that we don't necessarily have to write is the first power. But with these here, we'll go on and write it just so that we see it and we know that we are converting correctly. Questions, additional questions on these first two so far? C, log base 21 of 21 equals 1 would be 1 to the first is equal to 21. And the last one would be 1/5. You could put the parentheses. We don't necessarily have to. I would not. Is equal to 5. How do we feel about these here? We like these? All right, you ready to go the other way around? Now they've given us exponential. We're going back to logarithmic. So the b to the x equals y, if and only if log base b of y is equal to x. So log base 5 of 25 is equal to 2. I have a tendency to do that. For this here, we don't need it. We do it to separate it. We do need the 5 to kind of be dropped down, lowered. Now, this is something that I don't like with textbooks, or most books, most places have this. It's not just textbooks in general. They will write some of the equations like this here. That x and 2 are not together. It's log of x, and that is then added with 2. So if I put parentheses, this is really what the book is saying. So we're taking log base 5 of x and then adding 2 to it. The textbook will add parentheses when it's wanting to signify that the x plus 2 is together. If it's not, they'll just leave the parentheses and just assume that you know that they're separate. I think it's better to go on and just have either way have the parentheses so that we know for sure if they're together or not. We don't have to just assume based off the setup. It's one way or the other. Does that make sense? Now, like with the other ones, we can grab the calculator, right? Do log of 25 and we get 2, yes? Well, that's not 2. And the reason for that, there's actually a specific reason, because this log is what we call the common log. Because if you notice here, the base is not written. It's understood to be 10. If the base for a logarithm is not written, it's understood to be 10. Right, but it's not to the base of 5. So the button itself on both calculators is going to be to the base of 10, not to a different one. Now we will get ways to change the base, and we will learn that later on, and that is the change of base theorem, kind of named aptly. But we'll go over that later. So unfortunately, we will actually find a way to do this later today, to plug it in, but we won't do it for now. Okay? Now, if we look at the next one, 10 to the negative 1 equals 0.1. Log base 10. 0. Log base 10 of 0.1 equals negative 1. Well, as we just said, this is considered a common log. So if I grab the calculator and say log 0.1, we do indeed get negative 1. And yes, that also means that this here is the same as saying log of 0.1 is equal to negative 1, because the base of logarithms is understood to be 10 if it's not written. If it's any other base than 10, we definitely have to write in that base. Like our first one, log base 5. We have to have that 5 to signify what the base is. Questions on these here? Are you ready for the next one? 8 to the 2/3 equals 4. Log base 8 of 4 equals 2/3. That's not a common log because the base is other than 10. Even if the base was 100, it would not be a common log because it has to be specifically 10. You ready for the next one? 6 to the negative 3 equals 1 over 216. This would be log base 6 of 216 equals, equals negative 3. Yep. Questions on this here? Are you ready for the next one? 9 squared equals 81. This would be
Log base 9
of 81 equals 2. Log base 9 of 81 equals 2. The next one we have 20 to the negative 1 equals 0.05. This, as a logarithm, would be log base 20 of 0.05 equals negative 1. C, 16 to the 3/4 equals 8. Log base 16 of 8 3/4. And the last one, log base, 15 to the negative 2 equals 1 over 225. Log base 15 of 1 over 225 equals negative 2. Questions on any of these here, going from logarithmic to exponential or exponential to logarithmic? We feel comfortable with these here. And we will go back over these kind of again once we get some more of the properties of logs and how we can use and manipulate them and see that these hold true still, and we don't have to do this flipping kind of method. Not so much common, but we will be evaluating using common logs at a certain point. Now there's two key pieces of information. We won't use them so much now, but they are good to know. One of them is log base b of 1. Log base b of 1 is always 0. I think some in academics we talked about this. Now, we can't take the logarithm of 0, so b can't be 0 or negative. we can't have 0 or negative with logarithms inside. It just doesn't work. So what's inside, or the base also cannot be a negative or 0. Just does not work. We can't have those. And the other one is log base b of b. If the base and what's inside the logarithm are the same, it's equal to 1. And the reason for that is if we rewrote it in exponential form, we're saying b to a number is equal to b. Well, the only way that works is if the exponent is 1. Does that make sense? Same thing's true with log base b of 1 equals 0. Well, the only way I can have it something to an exponent at equal 1 is if that exponent is 0. We do have to add the stipulation that b cannot be 0. Just 0 to the 0 does not exist. It doesn't work. But we're going to evaluate each of these logarithms. And there's different ways we can go about it. And there's more ways that we can do this once we get the properties of logarithms and understand how they work. And especially with those two there. But for these first few, we're going to set this equal to x and rewrite it as an exponential. So log base 4 of 64 equals x. If we rewrote this as an exponential, it would be what? 4 to the x is equal to 64. So really what we're saying is 4 to what power is 64? So what do we think? Well, 4 to the 16 is?
Oh, no.
So we can try 4 to the 4th.
Oh.
Do you just have to guess on those, or is there a way to like?
So there is some ways, because we want to get the bases to be the same, because that's one method to do this, is that we could say 4 to the x is equal to 4 to the third, because we're really looking at 64 to try to get the bases to be the same. Since one is 4, we can try to get the other one to be 4. Well, it turns out to be 4 to the third. And we'll get this again later, but our one-to-one property says that if the bases are the same, both 4, the exponents have to be also. So that means here x is equal to 3. Let's look at the next one. Log base 5 of 0.2, and we're set it equal to x. So 5, 0.2. 5 to the x equals 0.2. So we're trying to see what value of x will make it be 0.2. Well, it might be helpful to see what 0.2 is as a fraction. 1/5. Okay. That's a little bit nicer to work with. It might not seem obvious why we did that, to go from decimal to fraction. But if I convert it from a decimal to fraction, I now have a fraction that has 5, yes? We went over this, or kind of mentioned this yesterday, but is there a way to move the 5 from the bottom to the top? Yes. Because we can move it to the top, but we have to do something to it. Because we did this with e yesterday, because we had e to the negative 6x.
So we're turning it negative?
Because the 5, whenever we move a number from the top of the fraction to the bottom or bottom to the top, its exponent changes from positive to negative or negative to positive. Normally, we do this if the exponent is already negative. Then we move it to the top or bottom to get it to be positive. But there's nothing that says that we can't do it the other way around. And the reason we do this is because now The bases are both 5, which means the exponents have to be the same. And the textbook for these here really is going through a guess and check, and we will go back through these again, especially when solving and working with solving problems and equations with the one-to-one property. We won't do it so much with logs because not the next two, but the third one, we'll see why. And if we want to check this, we can plug in the calculator. 5 to the negative 1. Well, works if I do 5 instead of 2. We do indeed get 1/5 or 20. Let's look at the next one. Log base 1/5 of 125 is equal to x. Exponential form would say what? 1/5 to the 1/5 to the x equals 125. Well, it'd be nice if they were both the same number, yes? The one on the left, it'd be nice if it was, instead of 1/5, we had it just as 5. And it'd be nice if the one on the right, we could rewrite it as 5. Because if we could, then we can use the exponents and them being equal. Well, the one on the left, we do have x. And if I move it from the bottom of the fraction to the top, the exponent becomes what? Negative. So it'd be negative 1 for the x. And this is a little weird, a little strange. Right. And it is going to become negative x, because we could have just said negative x. But powers of powers multiply, so it'd be negative x.
So how do we turn the 125?
So 5 times itself, how many times is 125? So it's not 5 to the 5th, so let's try again. What's another guess?
3.
3.
Okay.
So what does that tell us? Negative x is equal to 3. Divide by negative, telling us x is negative 3. So 1/5 to the negative 3 will give us 125. So 1/5 to the negative third equals 125. If we're going from a fraction to a whole number, or a whole number to a fraction, most likely that exponent is negative. Questions on this here? Question on anything we've done so far? We're ready for the next part. Log base 36 of 6 x to the x Well, looking at this here, and we've done this to both sides at this point, mainly the right side, the number without an x, we rewrote it as a number times itself, or number to a power, yes? Well, 6 is really simplified as it gets, yes? But can we rewrite 36 as 6 to a power? 6, what? 6 squared is 36, yes? So we could rewrite 36 as 6 squared to the x. Well, powers of powers multiply. telling us that 6 to the 2x is equal to 6 for a value of x. Well, our one side is 2x. What's our other exponent? 1. Because even though it's not written, it's understood to be 1, yes? What do we need to do to solve for x? Divide both sides by 2, telling us x is 1/2. Yes. Because whenever there's not an exponent written, it's understood to be 1. Mm-hmm. Anytime there's not an exponent written, it's understood to be 1. Because x to the first power would be x. Mm-hmm. Now we could check this here and see, because this seems a little weird. 36 to the 1/2 is 6. 36 to the 1/2 is indeed 6.
You just like that circle up of that over the edge. That's okay.
Okay, that's me. So,
Questions on this here? Go on and grab a graphing calculator.
you say that would be right.
Over the edge.
Over the edge.
Is it over the edge or over the edge? Yeah, over the edge. Yeah, I know.
Okay, you look like the bird from Thumbelina. Dress like it too.
He was smirking.
All right. We're ready to evaluate these. Now we've said already we can't just type log base 4 of 256 in the calculator because the base is understood to be 10. Now I had you get the graphing calculators intentionally. Now the first thing we're going to do is, after we turn it on, is hit math, our math button. And once we get here,
Where is that? Under alpha.
scroll down. Scroll down. And we find log base. And once you have that selected, hit enter. And if you notice for this one here, it actually gives us a spot to put the base value. So here the base value is 4. And our number inside the parentheses is 256. Because if we're given the base and the number inside the logarithm, this here will calculate it for us. So it tells us our first one, log base 4 of 256 is 4. We can look at the next one. Log base 8 of 0.125 is -1. Math. Log base. So our base this time is 1/3. Now, to get a fraction, we can go alpha y equals enter 1/3. And then we would have 27, which is yes. Because if we wanted to log base of 1 divided by 3 of 27 is still -3. And our last one here, log base 64 of 8 is log base 64 of 8.
Oh, yeah, I can see it's 6.
is 0.5 or 1/2. 0.5 and 1/2 would be the same. I would prefer, especially, I mean, for 0.5 is a nice decimal, so that works too. But if we get a repeated decimal number, I'd prefer it as a fraction over a decimal. So if we said log base 64 of, say, 4, we get 0.3 repeated. And for the graphing calculator, if we hit math, and the first one in the list is fraction, it'll convert it to fraction, which is 1/3. So log base 64 of 4 is 1/3. Questions on this here? We're going to do at least one of these here. Natural logs. Natural logarithms. The natural log, ln of x, equals y, if and only if e to the y is equal to x. The base for all natural logs is understood to be e. The base for any natural log is understood to be e. We don't write it because there is no changing the natural log's base. It's always e, no matter what we have. So here, when we have the natural log of 6 equals x, well, ln of x equals y, if and only if e to the y is equal to x. So for us here, if we rewrote this first one in exponential form, we would have e to the what? Because, well, our base is understood to be e. Now, our x and y, this is going to seem a little weird. X is inside the parentheses, yes? So what would its spot corresponding to the general form would be with our, would be our 6. Our y, which is outside, is our x. So when we rewrite this in exponential, e to the y equals x. Our y is now, so giving us e to the x is equal to 6. So if you notice, this is behaving almost the exact same with our logarithms, except our b, our base, is always e. So for our next one, well, x is 5a, and b is, well, y is b. Have it flipped. Y is b. So in our exponential form, we would have e to the b is equal to 5a. Questions on this here?